Thank you. I will begin with a word of prayer. Dearly Father, we, again, Lord, thank you for this opportunity we have just to meet together and study your creation. Just pray you'd help us to use this time wisely, Lord, that we glorify you in what we do. In your name I pray, Lord Jesus. Amen. Get out a sheet of paper, write your name at the top, and your notes should not be in front of you. One. So one is give a formula using a limit to carefully define the sum k equals 0 to infinity of a sub k. And two, calculate 1 minus 1/3 plus 1/9 minus 1 over 27 plus 1 over 81 plus ... I will give you guys until I get coffee. Sound good? You should be able to do this in about 2 minutes. Your name is on there. Make sure your name is on there and pass them to the aisle. I'll collect them. Even if you just got here and are writing your name on a piece of paper, that's still worth something, so do that. Thank you. Thank you. walked in. Fair enough. We can't be sure about this person. Possibly yes. Here. Yep, there's one. Nope. 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 Yeah. Nope. Yep. Nope. Nope. No. Nope. No. 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 Maybe. No. No. You guys counted the yeses for me. I lost track.
One.
Two.
Two, three.
He said two.
There's
Two and
maybe.
three.
Yeah, that was a maybe. It was two and maybe.
Nope. Nope. I forgot where I started. We maybe back around already.
Go until you find the answer.
No. Well, no. See, there's one. All right, so I think in total there may be 3 or 4 of you who actually know the definition of a series. How can you expect how can you expect to understand things I'm going to say today about series if you don't know the definition of series, right? You can't. This is my point. You need to study, you need to make sense of the things I said in the previous day before you go on. If you don't, everything I say here is just a bunch of meaningless nonsense. This means, it's not that complicated, the limit as n goes to infinity of the sum k equals 0 to n of a sub k. That's it. That's all I'm looking for here. This is equivalent to saying that S of n is defined to be sum k equals 0 to n of a sub k, and S of n converges. It goes to, well, let's say the limit. The limit then goes to infinity of S of n is also equal to this thing. But anyway, I mean, some of you have written things like, here's like something I saw in a bunch of papers. You guys have written infinity here. I don't know what that means. You're defining what you're defining in terms of what, it's just circular. I don't know what that means. The point is we're taking this n and we're letting it go on and on and on, right? So some of you, and this is another popular wrong answer, will write something like this, which is great, but that's just another notation for the same thing. That doesn't define it, that's just another notation. The reason that what I've written is a definition, originally, in the green, is because I'm giving you a precise description of what a series is in terms of the limit of a sequence, which is something we've already covered, all right? And has meaning independent of the series. Now this guy, I think if I had gone through and find out which some of you were right or wrong about this, I think that would have painted a rosier picture. I bet a lot of you got this right, right? So this is a geometric series, right? And what's the first term is 1, or the 0th term if you like. And what's the radius? Or the ratio, I should say. Minus 1/3, right? So that's like minus 1/3 squared. That's minus 1/3 to the 4th. So the radius is minus 1/3. So this converges, as we worked out yesterday, a over 1 minus r, which in this case is 1 over 1 minus a minus 1/3, which is what? 1 over 4/3? So 3/4 is the answer there. All right. Now, I'm going to try to keep giving these quizzes because I want to hold you accountable to understanding what we do today, tomorrow. You need to try to follow the class. If you don't, By the time we get to the next test, there's no hope. All right? And I do want you guys to survive this class. All right, so let's go on. And this is a question about something in particular. Any questions? Okay. So last time we calculated the geometric series and also the, oh man, where'd it go? Here it goes. I extracted chapter 12 from my book now. So we're good to go. We proved that the sum of convergent series was convergent, right? So we've made it all the way. I wasn't trying to follow the book, but I accidentally did. Let's see here. Oh well, forgive me for doing that. Theorem 12.25, and this is a big one, is the Nth Term Test. You know, this is a funny thing because it's almost as important to not apply this theorem as it is to apply it. I'll tell you more about that as we go here. If the sum k equals 0 to infinity of a sub k converges, I can't write this as k, sub k, sorry my k's are ugly, converges, then a sub k goes to 0 as k goes to infinity. You know, corollary, related thing. If the limit as k goes to infinity of a sub k is not equal to 0, all right, then the series with term a sub k, series k equals 0 to infinity, diverges. All right. So there's a theorem, and there's a related result, thanks to logic. Let me explain to you why this theorem is true. Oh, by the way, these quizzes are bonus quizzes. These are not going to, I mean, they're not in the syllabus, right? So where do they count? They're points that they're on top of the syllabus. So these are bonus. They only help you. I guess I should have told you that. But I'm afraid if I tell you that starting with, then you won't take them seriously. So do take them seriously, otherwise they'll become unbonus.
Are you going to give them every day?
I don't know. Possibly. Let's see here.
Sounds like fun.
Want to keep you guys on your toes. All right, so let's suppose, here's the proof. We want to suppose that this series converges, okay? What's that mean? Let's suppose it equals to L, where L is the real number, all right? Think about this. Then what's that mean? Then the nth partial sum, right? Which would be what? The sum k equals 0 to n of a sub k is a convergent sequence, right? This converges to L as k goes to infinity. What am I using? Oh, I'm sorry, it's n goes to infinity, right? This is the thing that goes to infinity, right? How do I know this? This is the definition of a convergent series, all right? Now here's the neat thing. What if we look at S n minus 1? What would that be? How are these related? By what? By a sub n, right? I mean, we have what? We have Sn is equal to an plus Sn minus 1, right? This is the relation between them? No? Let me look at it a different way here. If we look at Sn minus Sn minus 1, how's that go? I'll use the plus dot 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 notation for a second here. So this is like a0 plus a1 plus dot 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 plus a sub n minus 1 plus a sub n, right? Minus what? Minus a sub 0 plus a sub 1 plus dot 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 plus a sub n minus 1. So what happens when you take the difference of the n partial sum and the n minus 1 partial sum? Right. So everything cancels all the way up to here, and you just get a sub n. So what's the limit as n goes to infinity of Sn minus Sn minus 1? That should be equal to, right, the limit as n goes to infinity of a sub n, right? But what does this go to? This goes to L, right? What happens with n minus 1? If you feed n minus 1 into the partial sum, and if n goes to infinity, does n minus 1 also go to infinity? It does, right? So essentially by a simple substitution lemma, this goes to L as well, so we get what? L minus L, this is 0, right? So hence, the limit as n goes to infinity of a sub n is equal to 0. Because this thing, if you'll allow me to solve the style calculation, is 0. I could write less here, right? So this is sometimes called the Nth Term Test. You see why? We could study the Nth term. I mean, it's kind of, this is the same as saying what? So this is a very, very nice theorem for showing the series diverge. For example, if I have the sum k equals 0 to infinity of something like k over k plus 1, right? Well, then I can say, okay, so this has a sub k equal to k over k plus 1, right? And the limit as k goes to infinity of k over k plus 1. Oh, man. You guys you shouldn't let me do this. I mean, you're all here, so it doesn't matter to you, right? But the audio is a little bit substandard up to anyway, it's okay. There we go. I guess if somebody had the volume turned up right now, they're deafened. Anyway, so k over k plus 1. What is this? As k goes to infinity, what's this go to? This goes to 1, right? Is 1 0? No, 1 is not equal to 0, right? This is not equal to 0. So therefore, the sum k equals 0 to infinity of k over k plus 1, I can't write, diverges by Nth Term Test. By the way, something we could do to save ourselves writing, we could start doing some name calling. We could give this a name, like we could call this series S, right? And then I could say, instead of writing this, I could take this and instead write what? S. And that would save me continually rewriting the original expression. It's something I haven't started doing yet, but it does save you some writing. And because I do want you guys to be precise, all right? So when you use words like it converges, that rubs me the wrong way because I don't know, like, what are you talking about? You start having problems with more than one thing, that becomes ambiguous. It's important to be precise in our discussion here. So, yeah.
Is this theorem if and only if, or is it just?
I don't know. Let's see here. So that's a good question. Is this theorem if and only if? You know, let's find out. Now, if we draw a picture, we can draw a picture. There's a really cool picture we can draw. If you have a function, right, and it looks, I don't know, it could look like this. All right. The function I'm drawing is going to be continuous. All right. It's going to be a continuous function, and it's going to have limit 0. The reason it has to have limit 0 is pretty obvious from the Nth Term Test. What I want to do is I want to use this continuous function from 1 to infinity to study the corresponding series that has terms built from the function. So, like, I'm going to use this idea. The idea is to use the integral from 1 to infinity of f of x dx to study the sum, right, from k equals, well, I guess, stupid. I guess I'll do, see, I don't know. Now I get lost in the stupid indexing. Just a second. Let me set it up the right way. Stupid starting point choices. Well, I guess we'll look at, yeah. So we're going to start from 1. K equals 1. Yeah, fine. 1 to infinity of a sub k, where what? Where a sub k is simply the function evaluated at k. So if this is going to be a convergent, if this is the kind of function I want to look at as one that tends to 0, right? If the function doesn't tend to 0, this improper integral is going to diverge, right? And that's not too surprising. The corresponding series will diverge by the Nth Term Test. Now let's draw a picture. We can draw a picture here and relate some things. So here's 1, right? 2, 3, 4, and so forth. All right. Strange. How's it go? What does the series look like as it relates to the? If I want to draw a picture which described the area that corresponds to the series, what it would look like. So this right here, this height is a sub 1, which is f of 1, okay? This is the kind of thing I'm thinking about. This right here, right, would be, the height of this would be f of 2, which would be a sub 2, right? And so forth. Here's a sub 3, which is equal to f of 3. See how we're going with this? Now, what can you say about the area? Oh, man. Oh, doesn't quite match up, does it? Like, this is annoying. I want to start, I'm looking at the integral from 1 to infinity, you know? So I'm going to have to make a little bit of an adjustment. I can see this much, right? The integral from 1 to infinity of f of x dx, if this exists, right? If this converges, that's the area under the purple curve, right? That should be what? That should be above. That should be above what? Yeah, the sum k equals 2 to infinity, right? Of a sub k. Does that make sense? Can you think of anything else we could draw here? that would be above the integral and related to the series?
Did you go from 0 to 1?
Do what?
Left bound, so it would be going from
Like, sort of like turn my boxes over? Yeah. So like, instead do like this, right? And so forth. So this would be, you know, what's that? That's a, oh, it's again A1. So this would be less than or equal to what? Good grief. K equals 1 to infinity, right, of a sub k. By that picture. And this would actually make sense whether the integral of the function, I mean, if you want to think about it, if the integral of the function diverges, we still have this kind of like, I mean, you could replace this, instead of putting infinity here, you could look at you know, we could replace this with something like the sum k equals 2 to n of a sub k is less than or equal to the integral from 1 to n. Is that the right thing to do? 1 to n. Just a second here. One moment. I'll take your question here. So if I break this, try to think. If I get to n, I think this one goes to n because it's determined by the right endpoint, and here I have f of x dx from 1 to n, but that would be less than or equal to the sum, partial sum, k equals finite sum, really, 1 to n minus 1, I believe, of a sub k. If you think about it, because, so this one's determined by the, you know, determined by this point right here. I'm making a break in the graph, obviously. So we have this inequality between the nth partial sum of the series and the integral, just the plain integral from 1 to n of a continuous function. Is there a question? Yeah.
And so why does starting with k equals 1 make it from the left bound, and like k equals 2 makes it?
Just look at the look at the picture here. See if we've got a decreasing function, right? That's important. F continuous and decreasing on 1 to infinity. All right. Given that condition, in other words, my picture is reasonable. The red boxes. So this is A1. This is A2. A3. So A1 plus A2 plus A3 plus dot 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 dot. Right. But look at it. I'm ignoring A1. So I've got A2 plus A3 plus so forth and so on. These red boxes, you can ignore the A1 really. Just let me get rid of that box altogether. There you go. So let me this right here, you know. Over here, this last one. Goodness gracious, this one, right? These are always coming in under the purple line, which is y equals f of x. So the area under y equals f of x from 1 to n, right, is less than the area which is corresponding to the red boxes, which is A2 plus A3 plus A4, da da da, da plus AN.
But why are you choosing to draw the boxes under the curve when k equals 1? You're starting above the curve.
Those are the green boxes. The green boxes, right, different story. The green boxes, we're using the other point. We're using the, we're defining, so the red boxes take the right endpoint of the subinterval as the defining to fix the height. The green boxes take the left endpoint to define the height. So this height is A1. So this is A1 plus A2 plus A3 plus dot 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 plus AN. And that's this. Well, that's this.
Right. So how did you define that?
N minus 1, rather.
How did you define find that the green one takes the left endpoint when the red one takes the right endpoint? Just
That was the whole, I mean, that's the opposite, that's what we're looking at. I'm saying, look at these two different cases to find the boxes from the left or the right.
The height of the line, and like where F1 is, that's A1,
Mhm.
so that's the height of that box. So that would define what's that, is that A1.
I mean, my point is the left, I mean, basically the point is the left or the right endpoint rule, like L sub n and R sub n, we talked about with the study of the definition of the Riemann integral. One of them is above and one of them is below a decreasing function. So essentially this is the, let's see here, the right endpoint rule, and this is the left endpoint rule.
And you just chose to use them that way?
Well, the reason I'm doing this is we already have a theory for when these converge or diverge. And so this says that there's a comparison that can be made between the series and this improper integral. In particular, if the series converges, that forces what? That forces, if the integral rather, if the improper integral converges, that forces the series to converge as well. Right? On the other hand, if the improper integral diverges, it forces the series to diverge because it's also larger. This isn't exactly the series. How do you get the series? If I call this the S, this is what? This is actually just S minus A1, right? It's the series minus the first term. And this is what's known as the integral test. So this is a theorem, which is simply this, the sum, k equals 1 to infinity, a sub k converges if and only if the integral from 1 to infinity of f of x dx converges, given, and the conditions here is we're given f of x, f continuous and decreasing positive function on 1 to infinity. So if it doesn't converge, it diverges. So the other sort of half of this theorem I haven't written out, but I've said in words, is that if the improper integral diverges, then the series likewise diverges. This is the integral test. Its careful statement can be found on page 586 of your book. All right? And the proof really is this picture I just drew for you. Right? It shows you that the limit of this as n goes to infinity exists, forces the partial sum to have a finite limit. Conversely, if the limit as n goes to infinity of the integral diverges, by comparison, that forces the limit of the sequence of partial sums to diverge. So, now, Nathan asked me if this kth term test was an if and only if test. In other words, does it go both ways? All right, like if the kth term goes to 0, does that force convergence? Oh, if that were true. If that were true, life would be so much easier. Unfortunately, it is not. It is not true at all. And this is probably one of the top fundamental confusions of calculus students, is to suppose the converse of this is true, but it's just not. Here's an example. If you look at the sum, k equals 1 to infinity of 1 over k, right? Here we have a sub k is equal to 1 over k, all right? Now that clearly goes to 0 as k goes to infinity, right? Now if Nathan was right, or I mean he wasn't saying it definitively, he was asking a question, but if there was a converse to this kth term test, that would be enough. We'd be like, okay, the series converges. right? Notice, the convergence of the kth term is different than the convergence of the series. To say the series convergence is to say that the sequence of partial sums converges. What's the sequence of partial sums look like here? It's this. It's 1, then it's 1 plus a half, then it's 1 plus a half plus a third, and so forth and so on. It goes and goes and goes, all right? That's the sequence of partial sums here. Okay. The question is, does this converge to something? Or does it diverge as you go on and on and on? All right, let's let the integral test settle it for us. So what function do we compare to? Yeah, 1 over x, right? It's not, I mean, the integral test, while it's annoying because you have to calculate an integral, on the other hand, it's really not that surprising what you do. So we let f of x equals 1 over x. And now we need to pay our dues. Notice this is what? Positive? Continuous? And as f prime of x is equal to minus 1 over x squared is clearly less than 0, that implies that f is decreasing. Now there are other ways to argue that, but I'm arguing with calculus because I think you guys need to see it. Is decreasing on 1 to infinity. So we've got a positive decreasing function from 0 to from 1 to infinity, right? So it has paid its dues. We can apply the integral test. All right. So what's the integral from 1 to infinity of dx over x? So it's the limit. You're like, well, we already did this. I know we already did it, but let me just do it again. Integral from 1 to t dx over x, right? And what is that? So we got the natural log of the absolute value of t minus the natural log of 1. Natural log of 1 is 0. Natural log of t, what's happened to that? As t goes to infinity, this is what? Infinity. Right? So therefore, the sum k equals 1 to infinity of 1 over k likewise diverges. So this is an example, this is the quintessential example of a series which has a kth term which goes to 0, but the series does not converge. The kth term getting to 0 is a necessary, but it's not a sufficient condition to guarantee convergence. It's not enough. If it's not the case that the kth term goes to 0, game over, end of story, kth term test tells us our job is done. It diverges, which is super nice, right? So like, as you're studying a series and you're trying to decide does it converge or diverge, the first tool in your toolbox, the first thing you attack it with is the kth term test. You look at it, you say, the kth term isn't going to 0, it diverges. Game over, end of story. If the kth term goes to 0, well, that doesn't say anything. That says you got more work to do, right? Can you guys remember what we proved? What did we prove? We proved that the integral from 1 to infinity of dx over x to the p, right? What was this? This was convergent, and it was divergent when and when? It converged for what? For p larger than 1, right? And it diverged for what? For p less than or equal to 1. So I just re-derived the equals to 1 case, right? You can prove that f of x, right? Note, f of x equals 1 over x to the p has f prime of x equal to what? Minus p over x to the p minus 1, right? Which, by the way, is less than 0. So therefore, f is decreasing. And, it's positive, right? It's decreasing, and it's positive. It's continuous, right? Of course it's continuous. I took its derivative. It's hard to take a derivative if it's not continuous, isn't it? but you can. But not in traditional calculus. Sorry. I'll stop talking about other things. All right, so there you go. That means we can apply the integral test, and what does this tell us? This tells us now we have a whole bunch of examples, right? We can tell us we have a corresponding theorem that if we have the sum k equals 1 to infinity of 1 over k to the p, this is what? This is convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. This is the so-called p-series result. These are like fundamental examples. We always bounce off these examples. All right. Do you guys know what the name of the one I just did, the quintessential one? Did I say it? I don't think I said it yet today. What's the name of the p equals 1 series? It's so special it has a name. They don't all get names. Yeah, this is the harmonic series.
So is the end goal to be able to figure out if the series converges or diverges, and we just have to be able to show?
Is the our main task at the moment is to calculate the series if we can, which pretty much for us at the moment is either geometric or telescoping. We did some of those last class. And then otherwise, we're trying to understand when do they diverge, when do they converge, what theorems can we discover that tell us if and when they do, all right? So we're building a machine. We just have the first couple of cogs in the machine at the moment, but these are significant ones. So now that we have a standard bunch of examples, we can build new examples from these. All right, so there's a comparison theorem. Yeah.
Technically, there's not that well you can use calculus to prove that it diverges for p less than or equal to 1 because the derivative is larger than 0.
Oh, you're right. The logical connection from here to here only is good for, let's see here, for p what? This is for what? For p larger than 0, right? Very good. And so for p larger than 0, that gives us this. What do I do for p less than 0? How do I get the divergence for p less than 0 over here? Right. If p is less than 0, then 1 over k to the p goes to, which is, by the way, equal to what? K to the minus p, right? So we're looking at k to a positive power. What happens to that as k goes to infinity? K to a positive power goes to infinity as k goes to infinity. Thus, a sub k does not go to 0 in case p less than 0. So that's how you get the other. Thank you. I forgot about that. That's how you get the other half of the p-series result. That's a very useful comment. Thank you. Yeah, I'm only using the integral test to get the hard part of this theorem. The easy part of the theorem is when p is less than 0. In that case, we revert back to just stupid Nth Term Test. Yeah. If it's what? If p is negative a half, well then if p is negative a half, that means that's really the square root of p. So it diverges by, yeah. So, comparison. Theorem. And this is the direct one. The direct comparison. Here it is. If we have a sub n is less, oh, I'm sorry, we use k in here. A sub k, see, I learn series with sub n's rather than sub k's, so I sometimes regress to that. But your book uses k, so I try to use a k in here. If a sub k is less than or equal to b sub k, all right? And I think we need, well, then I think I need a 0 down here. So if you have 0, if these are positive terms, right, then the sum, a couple things, 2 things. Point number 1, you guys tell me what the result should be here. Number 1, if the sum k equals 1 to infinity of b sub k converges, implies what? I heard the sum, the first point number 1 is the sum k equals 1 to infinity of a sub k converges. We have winner. Anyone want to play part 2? If the series with smaller terms diverges, then guess what? The series with larger terms also diverges, right? So this is like direct comparison. The proof of this is not especially exciting, so I won't go over it, but it's just basically, there's a corresponding theorem for sequences, and it follows directly from that, basically. But anyway, yeah?
Will we need to be able to prove it?
No, you need to be able to use it. So for example, if I have the sum k equals 1 to infinity of, say, like 1 over k squared plus 7, right? I could think about my a sub k is equal to 1 over k squared plus 7, right? Which is, by the way, less than or equal to what? Well, it's just less than. 1 over what? 1 over k squared, right? Thus, convergence of the p equals 2 series
Why does b sub k equal 1 over k squared? You just chose it to.
right, well, the question is this a convergent or divergent series?
So you set up a situation in which it might do one, and if it doesn't do that, it's the other.
I got to make a choice. When I see that, I think, all right, so k equals 1, it looks different than k squared, right? But by the time I get to 1,000,000, what's the difference between 1 over k squared and 1 over k squared plus 7? It's pretty much the same thing, right? So what it looks like long term should more or less govern what it is. So a similar example would be something like 1 over, k plus 3. That intuitively, I know is going to diverge because that's really just a shifted harmonic series. But there I'd have to do some work because the inequality doesn't work out nicely for me just yet, But let me focus back on my original example here. The point is, this looks like a p equals 2 series, so I compare it directly to the p equals 2. All right. We'll learn a limit comparison test fairly soon, and limit comparison test will make this easy to compare to the harmonic series, if I remember right. Oh, fun fact. This is pi squared over 6. This was known to Euler in 1737, I think. The reason that is what I just wrote is somewhat mysterious. Anyway, when did we start this class? 3:45?
Yeah.
50 minutes of fast? We're good. So have a good day, guys. You can cut it off. Sorry I started late today. It's my bad.